The project, okay, I will start now. The project of cataloging Lavoisier's collection of instruments was outlined for the first time by Maurice Dumas, director of the Musée des Arts et Métiers, and Douglas McKee, professor of history of science at the King's College in London in the early 1950s. This was a time when Lavoisier's studies flourished, and when the most prominent historians of science of the time, such as Henry Gerlach and Charles Gillespie, engaged in extremely original research. Despite this ferment, Dumas and McKee, undoubtedly two great experts and historians, did not manage to carry on with their project. And only some 40 years later, Paolo Breni and I proposed to the Musée des Arts et Métiers to bring the catalogue to conclusion. This proposal, submitted in 1999, became reality only in 2015, and the book we have published with Brill in summer 2022 is the result of 7 years of research, of collaborative research, which involved, in addition to the two of us, a rich team of curators, restorers, archivists, photographers, and historians of scientific instruments. In what follows, I shall present in the first part a brief historical reconstruction of Lavoisier's collection, and which is the impact of its survey on the contemporary historiography. I shall then consider the historical meaning of the surviving instruments and what we can learn from them, both in connection to Lavoisier's approach to chemistry and more generally to the way we approach the history of chemistry and, I may say, the history of science in general. As it is well known, Lavoisier fell victim of the French Revolution in 1794. The motives of this tragic end had nothing to do with his scientific career, but instead of his main profession, which, up to 1791, was that of fermier général, a member of the tax agency charged to the crown to collect indirect revenues. The survival of Lavoisier's collection of instruments is paradoxically due to the political events which ultimately led to the execution of the French chemist on May 8, 1794. Despite the fact that in the last year of his life, Lavoisier had progressively abandoned his duties at the Ferme Générale, the dislike of this institution of the old regime rapidly made him one of the enemies of the French Revolution. His estates were in fact confiscated in 1793. On 6 February 1794, Lavoisier was still alive, a decree issued by the Convention Nationale ordered the members of the Commission, the Temporary Commission of Arts and the Commission of Public Instruction to inventory the confiscated properties. This is really a very overall decree. The commission charged with this daunting task was composed of several of Lavoisier's former colleagues at the Académie des Sciences and some of his most important instrument makers. Among the 32 members, we find the chemist Claude-Louis Berthollet, the clockmaker Ferdinand Berthaud, the mathematician Gaspard Monge, the naturalist Louis-Marie Richard and René-Louis Desfontaines, the physicist Jacques-Alexandre César Charles, the anatomist Vic Désir, and the instrument maker Étienne Lenoir and Nicolas Fortin, Lavoisier's assistant in his laboratory, Arsène France, and one industrial chemist, Nicolas Leblanc. All of them, with the exception of Leblanc, famous Leblanc of the Leblanc process, collaborated with Lavoisier on various scientific and technological projects. Many inventories of Lavoisier's laboratory have survived, and as far as I know, these extremely detailed documents provide us with the most comprehensive description of an early modern chemical laboratory, not only for Lavoisier, but of any early modern laboratory. The authors of this early catalogue were often experts and former colleagues of Lavoisier, adding further value to a rather exceptional view of one of the most important laboratories existing in Paris. On Lavoisier's laboratory, the historiography has long insisted on its uniqueness and on the astronomical cost of some of its apparatus, questioning its real historical representativeness. I shall come back briefly on this controversial issue. Let me begin with a quantitative overview of the laboratory drawn from this inventory. Now I really give you just the quantitative overview, but in the inventory, these are itemized and described in detail. As you can see, there were some 11 furnaces, 146 pneumatic vessels, glass vessels, a huge amount of glassware, retards, alembic, glass flasks, vases, and other recipients, 7,000. Also a very considerable quantity of earthenware, retards, cooker bits, tanks, steel, pelicans, 1,000 crucibles coming from Germany, France, and other Parisian manufacture, and some 122 precision instruments. Altogether, this sums up to around 10,000 items, a very considerable number. Lavoisier's laboratory has often been regarded as an extravagant and expensive site of experimentation. Those who have most emphasized on the lavish cost of Lavoisier's laboratory
have suggested... Marco, I'm sorry for interrupt. I'm sorry.
Yes.
But
yes.
We are not seeing the slideshow is not progressing. It's not going to the next slide. Yes. So we are in the first. We are seeing the first slide.
You're not progressing. This is not see. You don't see it.
No, we see the first one.
Yeah, just the first one.
I can't believe it.
Perhaps you must...
Why? Okay, now we are seeing. Okay.
Yes.
Yeah.
Let's do it like this. I don't know why. I mean, this is the first time. Well, let's keep it like this then.
Okay.
Okay.
Okay. Thank you.
Okay. Well, sorry for this. That you miss this. Well, I just show you Maurice Dumas and Douglas McKee, at least, so that you see the two people who actually, both of them, wrote their main work also on scientific instruments. Maurice Dumas, his work on scientific mystery, while they were working on Lavoisier's collection. So this is rather important details to say. This is about somehow the quantitative data drawn from the inventory. And here we go. Here we are. So those historians who have most emphasized on the lavish cost of Lavoisier's laboratory have suggested that the results of the large-scale experiments at the arsenal became famous due to the impact of the costly apparatus rather than the actual experimental results. These claims are based on the reading of very few primary sources, such as the following one by the apothecary Jean-François Demachy. Here it is, who strongly criticized Lavoisier's use of complex apparatus. I translate, what would we say of our current physics, one so simply pursued with the aid of practical instruments with so few complications? Do we not see it subservient to machines, countless jeers, gaudy embellishment that, with the excuse of offering higher precision, lead an honest observer to harbor greater doubts about the real success of experiments? Now, Demachy was a secondary figure in 18th century chemistry, Paris, and his voice on chemical matters was either unheard or criticized. Nevertheless, authoritative contemporary historians gave great credit to his writing and have insisted with strong emphasis on the lavishing and useless cost of Lavoisier's apparatus. Historians, French historians of the French Revolution and of science, Jean-Luc Chappé, very recently went so far as to claim that Lavoisier's laboratory practice transformed chemistry into a science sévère, a severe science, preventing the laymen, artisan, and women who prior to this revolution were able to access an open science, a mundane science, a sociable science, from participating. These positions are mainly rooted in the conviction that 18th century chemistry before Lavoisier was relatively simple in its experimental features, and that the most important discovery on the nature of gases were made with rudimentary instruments. In fact, the cost of maintaining a traditional laboratory, such as this one, in good order, was considerable, long before the discovery of gases. Glassware often broke, earthenware vessels were rapidly consumed, chemicals were not always readily at hand, and some of them, such as mercury, were extremely expensive. I would like to point out that most of the laboratories in Paris were run by apothecaries, people really making money out of their trade, and so they could maintain important laboratory. That the other also research laboratories were installed in porcelain manufacture. So about this idea of cheap laboratory where you can make discovery before Lavoisier, it's a rather legendary one, I think. In the chemistry of gases, without the use of new apparatus, most of which was derived from natural philosophy, it was practically impossible to conduct original experiments. Lavoisier's equipment could, in many ways, be compared to Torben Berman's in Uppsala, Baldassare Sage and Antoine Beaumet in Paris, and that of other natural philosophers such as Henry Cavendish, Felice Fontana, and Joseph Priestley, not to talk about Volta, Alessandro Volta. Such apparatus was quite expensive and had been so long before Lavoisier entered the scene. Having said this, there is no doubt that, towards the end of the century, Lavoisier contributed to the development of instrument making in chemical laboratories to a higher standard, and thereby became a key protagonist in making the science more precise and consequently more expensive. The process by which he achieved this reputation is quite complex, and it involves several aspects that should be taken into consideration. But let me consider the actual costs of Lavoisier's laboratory and compare it with those of two Parisian colleagues, fellow members of the chemical section of the Académie des Sciences, who opposed this view on chemistry. And therefore, they're usually regarded by historians as underdog in comparison to the great authority. The estimated cost of the apparatus found in Lavoisier's laboratory exceeded 27,000 livres, which, if we take inflation as a parameter, would be comparable to roughly 300,000 euro today. Although a few instruments were left out of the assessment, the revolutionary inventories compiled by professional instrument makers and chemists provide a good and fairly accurate overview of the real cost of Lavoisier's laboratory. Let us now consider the cost of two distinguished Parisian apothecaries, Baldassare Sage and Antoine Beaumet. Sage, contemporary of Lavoisier, they were born the same year, they made the same school, and they had the same teacher. Now, in the 1760s, Sage decided to specialize in mineralogical chemistry and began to put together a considerable collection of natural history specimens. He managed to attract the attention of King Louis XV, and he was elected a member of the Academy in 1770, and from then on, enjoyed the protection of the king. With this royal patronage, he was able to publish his chemical books at the Imprimerie de Monsieur, the royal printing house, without having to ask the permission of the Académie des Sciences. Moreover, he gained a fortune, which enabled him to take up residence in an elegant hôtel particulier, and was granted the astronomical sum of 30,000 livres for setting up the galleries for his mineralogical collection. 30,000 livres. Lavoisier's laboratory overall costed 27. This is already just as a preliminary, he got 30,000. In 1778, Sage was appointed professor of chemistry at the newly established École Royale des Mines at the Monet, with a yearly allowance of 6,000 livres. His palatial townhouse allowed Sage not only to keep his collection there, but also to construct the laboratory that must have been one of the most impressive in the capital at the time. Like Lavoisier, he owned several precision instruments, including one of Megnier's balance, and Megnier was the most expensive instrument maker used by Lavoisier. At the request of the king, the Minister of Finance, Calonne, gave Sage 40,000 francs to help him with the cost of adapting his residence for his laboratory and galleries. The sumptuous science and allowances eloquently showed that the cost of such laboratory was comparable, at least comparable, to that of Lavoisier. The cost of chemical laboratories, however, increased exponentially regardless of royal subsidies or individual fortunes, because no doubt Lavoisier was a very rich individual. A striking example is that of, of Antoine Baumet, who was neither rich nor enjoyed any patronage, but was one of the most influential experimental and industrial chemists in Paris. Although they refer to completely different social and economic background, Antoine Baumet's pharmaceutical and chemical laboratories, because there was more than one in Rue de la Coquillerie, became so important that when he was able to sell them in February 1780, when he wanted to retire, he sold them for 126,000 livres, nearly 4 times the total value of Lavoisier's laboratory. The reason why Baumet realized such a high price for his laboratory is not known, although he was certainly among the Parisian chemists most actively seeking to improve the existing apparatus, and with this shop had become the most important supplier of apparatus in Paris and France. Moreover, Baumet traded in all sorts of chemicals, including rare and expensive commodities such as platinum and mercury. If not extravagant, Lavoisier's apparatus was certainly innovative. As I already pointed out, Lavoisier had around 7,000 pieces of glassware in his laboratory, of which only a few hundreds have survived at the Musée des Arts et Métiers. A closer examination of these surviving items have revealed a striking variety both in shape and texture, 2 qualities which were hard to find in the glassware provided by the Parisian trade. Glassmaking is a guild in France as everywhere else, so this was a problem for innovative scientists to create innovation. Lavoisier's creativity, combined with his well-known drive for accuracy, is particularly evidenced by his early efforts to introduce precision measurement to pneumatic chemistry. This important field of investigation revolved around several types of apparatus and materials, which became central in chemical investigation. Historians have emphasized the role of precision balance, of pre-slip pneumatic throw, and Hale's pneumatic apparatus, but somehow neglected the innovation in glass apparatus and its pervasive presence in most chemical experiments involving gas. Moreover, chemists were in constant and at times sudden need of glassware. The shape of glass recipients changed radically with the investigation of gases, and chemists were extremely creative in testing the potential created by this malleable material. Lavoisier was no exception, and once he decided to work systematically on the nature of gases, he began to both conceive new glass apparatus and study the property of glass. As early as March 1773, Lavoisier conceived a recipient, a balloon to weigh gases by plunging into water. But it was not easy to have this kind of instruments made. The delivery of this apparatus was delayed, and the delay was due to the workman's slow pace, glassmaker. It is interesting that Lavoisier refers to the maker as to ouvrier, as workman, thus confirming that in 1773 there was no specialized maker of this kind of apparatus. At this point, he was still working in his residency Rue de Bonenfant in the Palais Royal, which was unsuitable for a large laboratory. After waiting for his balloon for nearly 2 weeks, Lavoisier was still not able to perform the experiments he had in mind, and the entries of his laboratory notebooks reveal a growing sense of frustration. With this in mind, and given the quantity and variety of glassware needed, it is likely that when Lavoisier moved to the larger residence at the Arsenal in spring 1776, he used the opportunity to set up a small glass-making workshop as well. Now, you can see that I have pointed out with a red circle what is thought to be Lavoisier's residence and laboratory, which was not his own property. He was a manager of the gunpowder of state, of the manufacture, and facing his own laboratory, there was also a refinery of saltpeter, which make it a very interesting context, because he could have access to a sort of industrial laboratory, and then he could build his own laboratory that it was a research. As you can see, the situation of the Arsenale was particularly because on the left you see the Bastille, and in fact during the hectic days of July 1789, there were a lot of cannonballs coming and falling around and very close to the Arsenal as well. So anyhow, he had the opportunity now to enjoy a larger facility. And the fact that he might, or that he probably set up a glassmaking workshop in his own laboratory is evidence on this kind of item, which is, as you can see, a wooden chair with setback and long horizontal armrests. This type of chair, introduced towards the end of the 16th century, was used by glass blowers. The blowpipe, holding an incandescent glass mass at one end, was placed transversely on the armrest. The glass worker used one hand to roll the pipe back and forth on the armrest. With the other hand, he shaped the plastic glass mass using appropriate tools. If necessary, at the same time, a crouch glass blower could blow air into the open end of the moving pipe. Lavoisier's chair is interesting because of its rather uncommon back, as shown in the plates of the Encyclopédie devoted to glassworks in Diderot and d'Alembert. As you can see, there is no back here. The need to produce glass instruments has already been pointed out by Jean Nollet, an expert glassmaker and Lavoisier's teacher. But Jean Nollet is also the most famous experimental physicist of the mid-century France. He was one of the most important maker of instruments in experimental physics, and his textbook in experimental physics, the Leçons de physique expérimentale, were translated into German, were translated into Italian, in Spanish, was one of the most popular, if not the most popular textbook in experimental physics. It's relatively unknown, the fact that Nollet was also and began his career as a glassmaker and a glassblower, but this is rather important because it demonstrated also during his lecture in experimental physics, lecture that Lavoisier attended, how to produce glass instruments. While the innovation in chemical glassware are very important, and I cannot really insist too much here, Lavoisier is just to remember for his precision instruments, and above all, for the calorimeter, the gasometer, and the precision balances. I will come back briefly on this later. But I would like now to focus more on the status of chemistry, of one of the most important elements of 18th century chemistry, that is fire, in order to understand how Lavoisier approached this kind of phenomena, and what which are the difference of his approach, that is not just his own approach, but of this new generation of natural philosopher and chemistry towards this element, the element of fire. During the mid 1760, when Lavoisier entered the scene, the most important chemical theories and experimental practice revolved around the elements of fire, or the definition around the element of fire. Stahl phlogiston theory and Boerhaave elements of chemistry were the two main frameworks in which 18th century scholars interpreted chemical reactions. In chemical arts too, the management of fire was probably the central issue which puzzles artisans with all sorts of problems. The construction of efficient furnaces and the production of resistant crucibles and refractory instrumentation were the main concern shared by almost all the arts and also theoretical chemists. However, both chemists and artisans did not have any efficient instruments to control this essential element. Only experience regulated the heat of furnaces, because the first instrument to measure with some degree of precision temperature up and beyond 120, 140 degrees was Wedgwood pyrometers, introduced in 1785. While there was some awareness that different bodies change their chemical state at different degrees of heat, Black and Lavoisier were among the first to study specific heat from a quantitative point of view. Up to the mid-1770s, most of the chemical phenomena involving fire, combustion, calcination, fusion, etc., were mostly interpreted from a strictly qualitative framework. From the very beginning of his scientific career, Lavoisier, where the experimental physicist and instrument maker Jean Ollet as his master, as I just said, became extremely dissatisfied with this approach. It might be then come as a surprise that from his earliest approach to chemistry, Lavoisier did not look at fire as a privileged element, but that he rather focused on water. I will specify briefly now this kind of approach. In 1764, at the age of 21, in a manuscript note, he wrote, "Water, this almost universal solvent, is the chief agent employed by nature. It is also the one I have adopted in my work." Lavoisier's laboratory work led to his presentation of two memoirs at the Académie des Sciences in 1765 and early 1766. These were the first two chemical papers he compiled. In his first memoir, Lavoisier proved that gypsum was a salt composed of vitriolic acid and calcaire earth, that is, sulfate of lime. Unlike German chemists, especially Pott, who had subjected gypsum specimens to the action of fire, Lavoisier preferred to dissolve the specimen in water, since this was a simpler and more natural method of analysis. This method was explained by the fact that Lavoisier not only wished to break down gypsum into its constituent parts, but also hoped to produce an artificial sample by recombining vitriolic acid and calcareous earth. With this in mind, in August 64, he began to use the hydrometer to achieve exact gravimetric measurement. So he substituted furnaces with hydrostatic balances. From then on, he used these instruments to measure the specific gravities of ingredients in a chemical solution, of course, whenever possible. In 1768, in his first memoir presented before the Académie des Sciences as a member of the Académie des Sciences, Lavoisier defended the originality of this approach with the following words: "It is to the art of combination that knowledge of the specific gravities of fluids can bring most light. This aspect of chemistry is much less advanced than we thought. We possess barely the rudiments of it. If it is possible for the human spirit to penetrate these mysteries connected to chemical combination, it is by means of research into the specific gravity of fluids that one may hope to achieve this. The quantity of real saline matter contained into two fluids to be combined, their mean specific gravity, with that of resulting from their mixture. In other words, the results of the same experiments repeated on the same mixture combined with all the others may produce a considerable quantity of data leading to the solution of the problem." You can see that it's really a very quantitative approach. It may be a coincidence, as one scholar has suggested, but it is quite interesting that exactly in the same period, during the campaign of gypsum experiments, for the first time, Lavoisier used the balance sheet method and compared the weights of reactant before and after solution and distillations. Whether or not this was a mere intuition, it was only by the systematic use of the hydrometer in wet analysis that enabled Lavoisier to make a continuous record of the specific gravities of the reactants. And this areometer, this hydrometer, was conceived and made by Lavoisier himself. You can see that it's bent on the right. because he lent this very instrument to his teacher, Rouel, just to test, to make him test it and to spread this instrument as a chemical instrument, not any longer as a physical hydrometer, but as a chemical hydrometer. As pointed out by Gerlach and other historians, it was only also during this experimental campaign that Lavoisier began to use systematically the thermometer, by which he detected significant variation of temperature of the reactants. He thought the thermometer was very important also to detect the variation of temperature during the reaction. On the basis of this observation in spring 1766, Lavoisier drafted 2 notes on the nature of the elements and of fire. In one, he concluded this: the elements enter into the composition of all bodies, but this combination does not take place in the same way in all. In this, there is a great deal of connection between air and the igneous fluid, the matter of fire. Both lose some of their properties when they enter into the composition of bodies. It is known, for example, that air ceases to be elastic and that it occupies an infinitely smaller space than when it was free. So you can see that here there is very interesting about air and combine air with body. There is nothing new, but it's new within Lavoisier's program. This kind of combination was directly related to change of temperature, or, as later understood, the specific heat of each substance. At this stage, however, Lavoisier was unhappy to combine his preference of wet analysis with the sole use of thermometer. Was happy to limit. Lavoisier used for this Galland thermometer early in his career. And Galland was one of the makers in Paris that made the most precise thermometer at that time. Lavoisier's preference for wet analysis over the use of fire is due to another no less important reason. The French chemist was keen to observe chemical operation and to follow all the phases of their unfolding. This is quite interesting because traditional chemists usually privilege the senses of smell and tact of that over that of sight. Undoubtedly, Lavoisier's background in experimental physics and his early education played a very important role. As in this discipline, sight and observation had to be mediated and helped by ingenious instruments correcting the weaknesses of the sense, Lavoisier became immediately aware of the complexity of experimentation. To make simple experiments, it meant to construct sophisticated instruments by which it was possible to obtain unequivocal results. This long prelude brings me to reassess Lavoisier's crucial experiments on combustion made in summer and autumn 1772 that led to what Lavoisier himself defined a few months later a revolution in physics and chemistry. The theoretical background of this experiment has been fully elucidated by Gerlach in 1961, but I might perhaps say a few words on its technical background that help us to enrich their experimental context. In summer 1772, under the auspices of the Académie des Sciences, Lavoisier took part to a first experimental campaign led by Maquet and Cadet, who were senior chemists of the section of chemistry at the Academy, with the use of the Academy burning lens. You can see the large burning lens aimed at the determination of the effect of very high temperature on a variety of mineral substances and precious stones. After noting that during these experiments, effervescences were produced and suspecting that air played a crucial part in this, Lavoisier suggested his senior colleagues to investigate the combination of air in solid bodies more systematically. The project was not followed up, but Lavoisier continued on his own to think about it. And early in autumn, he modified Hale's pneumatic apparatus for collecting gases, which he saw in the lecture of Nollet. However, instead of submitting diamonds and other minerals to the action of heat he opted to work with phosphorus and subsequently with sulfur and lead. With these experiments, Lavoisier showed that during their calcination, these substances, instead of losing their phlogiston, they gain weight, which was due to their combination with air. The ingenious experimental setup proposed by Lavoisier avoided the use of fire, because you don't see it. Of course, you see the ray concentrated of light, but they're converging and coming from burning lamps that, in fact, they still exist in the Musée des Arts et Métiers. Lavoisier owned burning lamps, which was a smaller format. And this kind of experimentation allow any observer to follow the combustion step by step. Heat and fire did and could not disappear from Lavoisier's chemistry, but their role had to change and explain through the introduction of new apparatus. I do not have the time here to describe the origin of the construction of Lavoisier's most famous instrument, the gasometer, but I hope that the theoretical and instrumental background that I guided young Lavoisier into the investigation of gases that I just sketched is sufficiently clear to understand the reason of the introduction of this complex apparatus, of which the gasometer represented the final apex. The construction of the gasometer was parallel and complementary to the construction made in collaboration with Pierre-Simon Laplace of the calorimeters. These iconic instruments follow the development of Lavoisier's theory of gaseous state, which was read in several memoirs in 1777. In a series of experiments made on vaporization of several liquids, water, ether, and alcohol in a receiver of an air pan, the French chemist demonstrated that they could be transformed, I quote, at temperature characteristic of each into a state of permanent elasticity, like common air. Permanent as long as the substance was held at or above the required temperature. Different bodies, then, had different capacities of heat, and observation that was made independently by several natural philosophers before Lavoisier, and that Joseph Black tried to demonstrate through a primitive version of a calorimeter. Lavoisier and Laplace apparatus, however, was the most accurate instruments created to this purpose, and its use was complementary to this experimental work on the combustion and on gases. The glimpse I just gave you, and I'm approaching the end, the glimpse of I just gave you on Lavoisier's collection in the 1790s, on how he used some of his instruments, now lead me to consider what happened to his apparatus after 1794, to this huge collection. I have shown you some common apparatus, some glass apparatus, chair, some more sophisticated, and I wanted to show you a few fragments, but as a part of a consistent program. Now I would like to discuss about the fate of a collection, because from the historical point of view, it's rather important. Historical collections we admire in museums are often the survivors of a long story of progressive loss and destruction. What has survived is the result of a natural selection through random circumstances. The collection of Lavoisier's instruments currently on display in one room at the Musée des Arts et Métiers tells one of these stories, and it reminds us of the complex vicissitudes that surround the construction and design of a museum. It also reminds us that over time, collection interacts not only with the spaces for they are destined, but also with the cultural and social milieu that adopt and use them for ever-changing purposes. This is a problematic thing that belongs to any kind of collection. Between 1794 and 1864, the collection stayed in the hand of Lavoisier's heir. First, in the hand of his widow, Marianne Pauls Lavoisier, who built a sort of museum in her beautiful hotel situated in the middle of Paris, as you can see here in the obituary by veterinary, medical veterinary, Jean-Baptiste Houssard, who really emphasized how she kept all the library and museum of her husband intact for so many years, nearly 40 years. Then the collection moved in the hand of the family, de Chazelle, in the Chateau at Lacanier. We did not know if during this move glassware was dispersed, but we are sure that the collection was certainly richer than the one which is now preserved in Paris. What is left now of the 10,000 items enriching Lavoisier's laboratory? Well, this is a sort of slide I can see as also the context that I wanted to explain, because as you can see, there are 680 objects, but in fact that number is rather fluid because of the catalog that Paolo and I have done, because this number refers to the inventory number. But in fact, inventory number throughout this 2nd century refers to fragments. And we managed, especially thanks to Paolo's skill, to reassemble instruments or objects that the use of which was unknown or has been unknown for decades. And 3, 4 different inventory numbers became one apparatus, one instrument. So let's say that there are more than 600 objects that, as you can see, have been subjected to systematic restorations and a photographic campaign that helped us to reconstruct about 5 or 6% of what was the original laboratory. These instruments are mostly Lavoisier, but a few are domestic and belong to Madame Lavoisier. And again, a few of them belong to Madame Lavoisier's second husband, who was the American philosopher and philanthropist, physicist Benjamin Thompson, Count of Bramford. And these instruments are the only known existing instruments, calorimeters, especially related to calorimetry. Now, I would like to show you the last 2 slides showing a bit what kind of instruments are represented in this collection. As you can see, there are collections testifying to Lavoisier's interest in metrology, especially connected with the reform of weights and measure during the revolution that led to the decimal system, and Lavoisier had a very prominent role. There are surveying and mathematical instruments, not many, but surely used by Lavoisier because of his geological interest, especially for surveying. And not surprisingly, we see 3 classes of instruments that are very important. Natural philosophy, dominated by the study of electricity, air pumps, and mechanical models. There are meteorological instruments, including barometers, not only thermometers, really a great quantity of them, some of them extremely accurate, the best of the art at that time. And then, not surprisingly, chemistry with 250 items. There are some miscellaneous items and still 58 fragments of glass tube, stand, and other part of apparatus we were not able to identify. Another feature of the collection that make this collection very interesting is that represented by the 102 instrument maker and suppliers that signed or attested in this collection. Most of them were Parisian, but as you can see here by this trade card, some of them were living and operating in other French cities, such as the Italian instrument maker Scanegatti, were based in Rouen, and from whom Lavoisier bought 2 spring bands. To which extent, and here I really am about ending, to which extent this collection is representative of Lavoisier's original laboratory? There is no doubt that the figures I have shown provide a very significant, we think, overview of Lavoisier's attempt to apply the methodology of experimental physics to chemistry. If you cross the data with those available in his printed works and in his laboratory notebooks, we may notice a consistent attempt to raise the precision of chemical apparatus and experimentation. I cannot address here the complex question whether these highly sophisticated instruments are the effect of a literary technology, a material campaign of persuasion. Sometimes they are, or more often the genuine and constant effort to surmount an experimental methodology which was proving both expensive and inconclusive, that of his contemporary, expensive and inconclusive. However, the emphasis that recent historiography is putting on the historical relevance of the instrumental and material sources of science cannot longer ignore the philological necessity, as well as we usually do with I see. Let's see. Okay, that we need the same approach, the same philology that we apply to archival and printed sources. We can no longer talk about instruments on the basis of what we find on them in books or in manuscripts, but we need to learn to study them in the historical context of their making. The interesting stories told by Lavoisier's instruments are waiting to be explored, and the catalog that Paolo and I have produced will hopefully open the gate to a renewed interest in a truly unique collection. Thank you.
Thank you very much for your talk, Marco. This great, interesting talk where we could learn more about the path of the Lavoisier's instruments. That was brilliant. Thank you very much.